Okay, good morning, afternoon, or evening, everybody. Welcome to the Sentinel-1 on-demand radiometric terrain-corrected processing generating analysis-ready SAR data with ASF Vertex Earth Data webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Time, so we are going to go ahead and get started here. First, what I'd like to do is just go over a few webinar logistics. To ensure the best audio experience, participants have been muted. So if you have any issues or you have any questions, please enter those into the Q&A pod, and you'll find that located on the right side of your screen. This works like a chat. Today's webinar is being recorded. The recording will be posted both to our online Adobe Connect webinar catalog, as well as to our NASA Earth Data YouTube channel within a few days of completion. Once completed, I will send an email to all the registrants, and I will include both the direct link to the recording and also the YouTube link to the recording. As far as timing is concerned, today's webinar will be 1 hour long, with 45 minutes allocated to the presentation and live demonstration, and an additional 15 minutes for the question and answer period. What I'd like to do next is pull up today's agenda. Give me just one moment here. All right, hopefully everybody can see that. All right, our speaker today is Heidi Christensen. She is a GIS specialist at the Alaska Satellite Facility Distributed Active Archive Center, or ASF DAAC. She will begin today's webinar with an introduction to ASF, synthetic aperture radar, or SAR data, and radiometric terrain correction, or RTC. From here, she will transition to a brief overview of on-demand processing through the Vertex Data Access Portal, which is available at ASF DAAC. After this, she will begin a live demonstration, excuse me, where she will take you through the process of searching for data, submitting it for processing, and then finally accessing and downloading the RTC products. After our speaker has finished with her presentation and live demonstration, what we'll do then is we will move to a final optional set of polling questions. And then generally, I'll give these questions anywhere between 3 to 5 minutes or so. And then from there, we'll transition directly to the question and answer period. Depending upon the volume of questions that are received today, we will extend the Q&A period an additional 15 minutes from end time for those of you who may wish to stay on the line or are able to stay on the line, but we will have a hard cutoff at 3:15 p.m. Eastern. And then just one final note about questions. During today's Q&A session, we will try to answer as many questions as possible during the time allotted. But if for some reason we do not get to your question, our speaker will follow up with you offline after the webinar. With that, it is my pleasure to introduce today's speaker, Heidi Christensen. Heidi? And Heidi, I don't know if you want me to pull up the links pod first before you get started sharing your screen, and you can say a few words about that.
Sure. Thank you, Jennifer. As I go through the presentation, I will be referencing links to various resources, and these are all listed in the persistent links pod that Jennifer has displayed. So you can access these at any time. They will be referenced at certain times during the presentation, but they will be available through the entire presentation. And just a quick check, can everyone see my slide deck?
I can see your slide deck.
Perfect.
Everybody can hear the audio okay? All right, great. Thanks, everyone.
Excellent. I'm really excited to tell you about the new on-demand RTC processing capabilities that we now have available directly in the Alaska Satellite Facility's Vertex data portal. The Alaska Satellite Facility is one of 12 distributed active archive centers that provide data and support services for the Earth Observing System Data and Information System. Each one of the DAACs has a specialty, and we specialize in synthetic aperture radar data. We maintain NASA's archive of SAR data, which includes data that NASA collected itself, but also data from partners such as the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency. We serve datasets that are easy to access and free to use. One of the main benefits of synthetic aperture radar data is that it can penetrate cloud cover. This allows us to collect data during natural disasters, for example, if there is a hurricane or wildfire that has a lot of cloud or smoke cover, or also it allows for collection of data of the Earth's surface in areas that have frequent cloud cover, such as equatorial regions or in southwest Alaska, where there are very few cloud-free days. SAR is not sensitive to light availability. It creates its own illumination, which means that it can collect data at any time, day or night. With the addition of SAR sensors to satellites, we now have global coverage with SAR data, and newer constellations have frequent and regular imaging patterns that give a dense time series. SAR can collect data in different polarizations, which tell you different things about the Earth's surface. Some sensors are set up to just be a single pole sensor, which means that they send out in one polarization and can only receive returns that are coming back in that same polarization. So if it's sent out in a vertical polarization, only the vertically polarized returns will be sensed, which are VV returns. If it's sent out in a horizontal polarization, only the horizontal returns will be measured, or HH. Many sensors are set up to be dual pole, meaning that they can still only send out in one polarization, but they can receive returns in both of the polarizations. So if the signal is sent out in a vertical polarization, it receives both the vertical returns, but also the horizontal returns, giving you the VH polarization. Similarly, if it's sent out in horizontal, it receives both the horizontal returns and the vertical, or the HV. There are also sensors that can collect full quad pole data, which means that you have the VV, the VH, the HV, and the HH, which is a very powerful data set. There are costs, however, and trade-offs in collecting a full quad pole data set, and so it's not so common to have full global coverage with a quad pole sensor. SAR is sensitive to very small changes in elevation on the Earth's surface, which makes it an excellent tool for monitoring surface deformation, either caused by natural processes like earthquakes or volcanoes, or human processes such as mining or construction. I'd like to mention a few key components about the acquisition of SAR data. First of all, SAR makes use of the microwave range of the electromagnetic spectrum. These waves have a longer wavelength than infrared waves, but they're shorter than radio waves. SAR makes use of an active imaging system, which means that there is a signal that is sent out from the sensor, it travels down to the Earth, and only the returns of that controlled signal are measured. And lastly, SAR makes use of a side-looking geometry. This means that the signal is always being sent down at an oblique angle to the Earth's surface. This is necessary in order to process and interpret the data correctly, but it does mean that there are certain distortions that are inherent to SAR data sets. You need to be aware of these distortions and be familiar with the corrections that you would need to apply in order to use SAR data in your particular application. There are two components of SAR datasets, the amplitude and phase. I don't have time to go very deep into these details, but we did give a webinar this past summer that gives a bit more of an introduction to SAR data. If you're interested in accessing that resource, there is a link that's listed in the Persistent Links pod, and you can visit that and watch that webinar to go a little bit more into detail on these concepts. The amplitude component is how much of the signal that's sent out actually returns to the sensor. That's also called radar backscatter. The amount of backscatter is impacted by physical and dielectric characteristics of the scatterers on the Earth's surface. The dielectric characteristics are essentially the absorptivity of a scatterer on the Earth's surface. So if a scatterer has high dielectric properties, there's a greater chance that it can return more of that signal to the sensor because it reflects the signal better. Whereas something that is more absorptive absorbs more of that signal, so there's less potential to be returned to the sensor to be measured. However, the physical characteristics also come into play. Let's consider a freshwater lake. On a calm day, a lake surface will be very smooth, and water has very high dielectric properties. So if the signal is coming in at an oblique angle and hits that nice smooth surface, it will be reflected off very effectively, but the signal travels off in the opposite direction from where it came from. So you would expect returns over a lake to be very low. Most of that backscatter just is scattered off into the other direction. Very little, if any, comes back to the sensor. If you look at this image that's displayed on the screen, you can see some of these lake areas with very, very dark returns. Different polarizations interact differently with scatterers. So the VV polarization is particularly sensitive to surface roughness. So if we think about that same lake, on a calm day it's very smooth, but on a windy day that surface can become roughened, and there may be waves that have an appropriate angle where the signal would hit the wave and actually be sent back towards the sensor. So on a windy day, you actually get much higher returns from a lake area than you would on a calm day. On the other hand, VH polarization is more sensitive to volume scattering. A common volume on Earth is a vegetation canopy. It's a kind of a thick layer that allows some of the signal to pass through and interact with lots of different parts of that vegetation canopy. So it might hit some leaves and stems and kind of get bounced around. And in that process, the signal can become depolarized. So instead of still being in a vertical polarization, it can be sent back in a horizontal polarization instead. So over a vegetated area, you would expect higher returns in the VH polarization, and lower returns from surface, from areas that are not volumes, just a plain surface like that lake. Even on a windy day, you wouldn't expect VH returns from that lake because even though it's rough, it's still a surface, so it's not decoupling that or depolarizing that signal. The phase component is the location of the signal along its wave cycle when it returns to the sensor. So this can be used as a proxy for distance between the sensor and the Earth's surface, and this is the basis of SAR interferometry. If you take an image from the same place in space over the same area on Earth on two different occasions, you can compare the phase returns from those two acquisitions. And if there are differences, that will indicate that the distance between the sensor and the surface has changed in that period of time. So if there is subsidence, the wavelength will have to, the wave signal will have to travel farther, and so it'll be further along in its wave cycle when it returns to the sensor. Whereas if there's been uplift, the surface is closer to the sensor, so it doesn't have to travel as far. So the phase will be earlier in its wave cycle when it returns. For today's presentation, I will be focusing on the amplitude part of the SAR data set. But I did want to mention the phase component. If you're interested in learning more, another great resource is the SAR handbook, which is also linked in the Persistent Links pod. It's a free publication that's available online, and it gives a great introduction to SAR and also has real working examples of how you would use SAR in real life. And there are tutorials that you can actually get your hands on the data and work through and learn more about working with both amplitude and phase data. Today we'll be working with the Sentinel-1 dataset. Sentinel-1 is a European Space Agency effort that's part of the Copernicus mission. Sentinel-1 gives global coverage with C-band SAR using a two-satellite constellation. The first Sentinel-1 satellite was launched in 2014, followed by Sentinel-1B in 2016. Each one of these satellites has the same orbit cycle, and it returns over the same place on Earth every 12 days. But the orbits are offset from each other by 180 degrees, which means that you actually get coverage over the same part of the Earth every 6 days. Now that's just the potential for coverage. It may not acquire every 6 days. Most places on Earth will still have a 12-day repeat cycle, but there are some areas of interest that will have a 6-day repeat cycle, particularly in Europe, or if there are specific concerns that would drive a more frequent acquisition. Because these are polar orbiting satellites, the polar regions actually tend to have denser coverage because a lot of the paths overlap as they approach the poles. So you can actually get quite dense time series in some polar regions. New data is available to download within 3 days of acquisition, and most often it's available within 24 hours. It's free and easy to download from ASF in multiple formats. The two most common formats, and what will be useful to most users of SAR, are the GRD, or ground range detected products, and the SLC, or the single look complex products. If you will be doing interferometry with the dataset, you will need to use the single look complex dataset because that still retains the phase data. The GRD is really focused on the amplitude part of the dataset, so it no longer carries the phase information, but it's been consolidated into one simple image. So the single look complex, if you were to look at it, pull one of these data sets into a GIS, for example, the corners would appear in place, but it would be kind of squashed in because each radar burst that makes up that image actually overlaps the next one. So if you were to look above and below the boundaries of each burst, you would see that there's data that's repeated. So all of that data is still contained, and you can process that as you would like. But with the GRD, it has already been processed for you so that all of those overlapping data sets are averaged together. They've been multi-looked to give one cohesive product. It's a much smaller file size, so if all you need is the amplitude data, the GRD may be a good choice. That said, either a GRD or an SLC can be processed through to an RTC product. Radiometric terrain correction, or RTC, is a process by which we correct for those distortions that are inherent to the SAR dataset. And this is caused by that oblique look angle. If you look at the image on the left, you can see that the mountains outside of Juneau kind of look like they're squashed over, and the front edge is really bright. So this image was acquired from the left side of the image, so the satellite would have been flying to the left and acquiring data down to the right of itself. So the slope of the front side of the mountain is such that when that oblique incidence angle is hitting that slope of the mountain, you're getting returns from near the top of the mountain at the same time as returns from near the bottom of the mountain. So they're all coming back kind of around the same time, which is interpreted as being all from the same place on Earth. So that signal kind of compresses the front side of the mountain. And not only does it distort the terrain itself, but it also results in that false bright return of radiometry. So what's happening is that all of the returns are coming back at once, and they're interpreted as being from one small area. But really, that backscatter is from large areas of that slope. And so there are all these scatterers that are contributing to that signal, but it's all being kind of interpreted as being from one small area. So radiometric terrain correction uses a digital elevation model to, first of all, move the terrain into place. So the tops of the mountains are stretched over so that they appear where they should be in space. But also, there is a normalization of that radiometric backscatter so that the returns actually represent the amount of surface area that was contributing to that return. So if you look at the image on the right, you can see that looking straight down now at the image, the mountains are where you would expect them to be, and the front sides and the back sides of the mountains are much more even in their radiometric returns. SAR data can be difficult to process. It's a large data set, so it requires fairly significant computing resources, and it also requires specialized software. If you're new to SAR, it can be difficult to know the workflows that are required to generate an analysis-ready product from a GRD or an SLC. As part of ASF's mission to make SAR data more accessible, we've been developing automated workflows for generating analysis-ready products. We introduced HYPE, the Hybrid Pluggable Processing Pipeline, in 2016. This platform allows us to leverage cloud computing, which is an efficient way to deal with these large data sets. And we've been using that to develop standardized SAR processing workflows. HYPE has been in beta, meaning that interested users can have access as long as they give us feedback on the products, but it hasn't really been open widely to the public. But with this effort, we've taken our RTC processing workflow from that beta environment and integrated it directly into Vertex, which is ASF's data search user interface. Now all Vertex users can generate Sentinel-1 RTC products directly within the Vertex platform. At this point, we just have our RTC product available, but we are working at integrating more of our beta products into Vertex moving forward. Our current RTC product was processed using Gamma software, which is a commercial SAR processing package. The output files are packaged into zip files that include geotiffs of the actual RTC products, which are shown here in the list. There is an RTC product for each of the polarizations available for that data set. But you can see that there are a lot of other files included. If you're new to our products, I encourage you to look at the README file that's included in each one of these product packages. It goes through all of the files that are included and tells you what they are and how they could be potentially used. In addition, each raster has an XML file associated with it with specific metadata for that raster. If you are an ArcGIS user, you can actually access the data in that XML through the item description in ArcMap or the metadata tab in ArcGIS Pro. While Sentinel-1 has global coverage, our current RTC dataset we don't have the capability to generate RTC everywhere on the globe. And this is a limitation of the digital elevation models that we are currently using in our workflows. So at this point, we do not have the ability to generate RTCs over Greenland or Antarctica or north of 60 degrees in Eurasia. So in the future, we are hoping to integrate the Copernicus DEM, which would then give us full global coverage. So stay tuned. We're working on integrating that into our platform. In order to access on-demand processing in Vertex, there are only two requirements. First of all, you will need Earth Data login credentials. The Earth Data login is a single login credential that is used across NASA's DAACs. So many of you may already have an Earth Data login credential if you've used any NASA data before. If you don't already have these credentials, you can visit the Earth Data website and sign up. It's free and it's a pretty quick and easy registration process. Once you have Earth Data login credentials, the first time you visit the Vertex portal, there's an option to sign in. And that is where you enter those Earth Data login credentials. And the first time that you do that in Vertex, you will be prompted to accept the ASF End User License Agreement. You only need to do that the first time you log in, and then it's saved in your profile. Once you've done these two things, you are ready to order and download data. Before I move into the live demo part of the presentation, I would like to mention a few resources that we have available that essentially walk through the same workflow that I will be showing you in the demonstration. We have a quick start guide, and we also have a video tutorial that's available directly on the Vertex website. So if you select the menu and click on Video Tutorials, if you scroll down to the bottom, under the Advanced Features section, there's an on-demand processing option. And that opens an interface that has a video as well as screenshots that describe the main steps of the process. There are links both to go directly to this interface within Vertex, and also if you just want to get to the YouTube video, there is a link for that as well. And those are also in the persistent links pod of the Adobe Connect interface. Lastly, we do have a story map tutorial that walks through this process as well. It's step by step. There's a slideshow that takes you through every part of the process of searching, submitting an order, and then downloading the data. But it also puts it in a little bit of a context in terms of interpretation and use of that data. And it links to additional workflows that walk you through how you would potentially use RTC data in a GIS workflow. So if you're interested, I invite you to take a look at that story map. And with that, I will launch ASF's Data Search Vertex portal. The first thing that we'll do is sign in. Now, because I've signed in recently, it actually remembers my credentials. But if you were signing in for the first time, you would enter your username and password for your Earth data login, and it would take you to a signed-in status. We'll be doing a geographic search and looking for Sentinel-1 data. At this point, our RTC processing is only available for Sentinel-1 data sets. We do have other data sets available, and you're welcome to check those out, but they are not suitable for our on-demand processing at this point. Sentinel-1 is actually the default data set that you will see when you open Vertex. It's our largest data set and also our most frequently accessed. If you have an area of interest already, either a shapefile or a GeoJSON or a KML, you can actually import that directly from your computer and start with that. Otherwise, you can simply set your area of interest directly in the map interface. You can drop a point or you can draw a line. You can do a simple box draw, which is the default. Or if you want to do a more complex polygon to cover just particular areas, you can also use that. Once you've set your area of interest, there are additional filters as well that are worth considering. As you add more filters and your area of interest, you'll see that there's a tally of how many files would be returned if you ran the search at that moment. So at this point, there are over 10,000 files that meet our criteria. So we may want to apply some additional filters. You can set a search date. So if I'm just interested in data from this January that just passed, I can set a date range for that month. Or if you're interested in a seasonal search, meaning that you want to see the data from the summer period every single year that data is available, you can just set a start day and a season end day, and it will search for anything between those two dates regardless of the year. You can also restrict your search based on the file type. As I mentioned, either GRDs or SLCs are suitable for generating an RTC product. Currently, we support SLCs and GRDH products, so either the GRDH, GRDHD or the GRDHS. The H indicates high resolution, and the D indicates that it's a dual pole data set. Most of Sentinel-1 data sets since the launch of Sentinel-1B, so since 2016, most of them, if they're overland, they will be GRDHD. So if I select that, I can see that there are 23 files that would be returned. If I click on the single pole, which means that it's just VV or VH, you can see that that actually doesn't change the number of files. There aren't any that were collected in that mode over my area of interest. If I select the single look complex option, you can see that it doubles the number of files that are available. I'll just search for all of the potential file types. And you can see that I get a list of results. If I click on a result in the results panel, it will show the footprint of that result in red on the map. So if I'm looking through and I find a scene, say this one, that covers an area of interest particularly well, I have the option to restrict my search to just show the images that were collected over this footprint. So if I click the More Like This button, it will search for only the results that had that same path and frame. So here I have just two scenes that come back that are both over the same place on Earth. So this is a pretty powerful tool for generating time series. Once you've found the data sets that you're interested in, you can add them to your on-demand queue. And that you can do using this icon here. I can either select it individually, and you can see that there's the option to add an SLC, or there's also the option to add a GRD. This icon will only show up for the product types that are available for generating an RTC product. So if the SLC and the RTC products, in most cases you wouldn't want to process both of them, they will give you essentially a very similar data set, but there are some slight differences. For example, the SLC tends to have a little bit more coverage in the along track direction, so at the top and bottom of your image you may get a little bit more data. So if that's important, that would be one consideration for an SLC. The GRDs have been clipped down to a nice smooth rectangle rather than having jagged edges. In addition, because the process of multi-looking is different for the two products. The GRD, as I mentioned before, has already been multi-looked, or some of the pixels have been averaged together in advance, whereas the SLC, when you bring it in and start processing, it hasn't had that same multi-look approach applied to it. So there will be slight differences in the way that things were averaged together. So if you're curious which one works best, or if there's a significant difference that you see for your application, you can just add one of each to your queue and take a look and see what the difference is. Another option, if you have reduced your results to a state where you want to add just everything to your on-demand queue, you can also use this bulk on-demand feature. It will ask you if you want to add the SLC or the GRD jobs. I'll select the GRD jobs, and you can see that up here I now have 3 items in my cart. Now it's 3 because I already had added a couple, but one of them was a duplicate of the one that I selected from the bulk on-demand add. So it will look and see if there's any duplication in the input granules and only keep the ones that are unique. So if I visit the on-demand queue, I can see that I have 1 SLC that's loaded up and 2 of the GRDs. If I decide that I actually don't want to process an SLC at this time, I can just remove that job from the queue. And I can close the queue and go back and continue searching if I want to add more before actually submitting it for processing. Once you're ready to process, you can enter a project name. If you start typing, you can see if you've added project names before, they will show up, and you have the option of reusing one of your names. And this is an easy way to bundle all of those products together under one project name, making it easy to search for your results. So I'm going to select the Michigan demo. And then you have some options in terms of the parameters that are applied to the processing. So you have a choice of radiometry, gamma naught or sigma naught. If you have questions about what these are, there is a question button next to each of the parameters that allows you to get a description of what this is. You have the option to choose either power or amplitude scale. Power scale is often used for statistical analysis. But if you bring a power image into a GIS or look at it in an image viewer, it will generally appear very dark. The power images have a very wide dynamic range, but most of the values are actually very close to 0. And so you'll get a kind of a skewed grayscale where everything looks very dark, and often you can't see any actual features. If you're interested in the data more for the imagery aspect of it and are looking at it more and visualizing more, you may prefer the amplitude scale. You can adjust the stretch for either of these if you're working in a GIS or by adjusting your dynamic range. But in general, power is great for statistical analysis, but amplitude may be more accessible for just looking at. So I'll choose amplitude. And then there are a number of other options. You can choose to apply Dem Matching, which we don't recommend if you're doing a time series analysis. This process, so the Sentinel-1 data is the orbits are very precise. And so the data sets are actually georeferenced very well. And if you apply Dem Matching, it kind of moves over the image from its georeference location to match the digital elevation model location, which, because we're using global DEMs, often they aren't the best in terms of the geolocation. So you might get a better, you might optimize your RTC results more if you use Dem Matching, but if your main focus is to look at changes through time, for example, it's better not to use that because you'll get a much more consistent data set if you don't apply the Dem Matching. But if you just have one granule that you're interested in looking at and want to kind of maximize your RTC returns, that it may be a viable option to add that. Again, if in doubt, you could order one of each and see how it impacts your particular data set. It will be really different depending on the terrain and the conditions of the image. You can choose to include a copy of the digital elevation model that we use to generate the RTC. Now, this is not a stand-in for a regular digital elevation model. We use publicly available digital elevation models like the National Elevation Dataset in North America or the Shuttle Radar Topography Mission. And we apply an ellipsoid correction. So if you were to use this digital elevation model to do a height analysis, you would find that it's different than what you would get if you use the actual source data. So if you are interested in a digital elevation model to use as a digital elevation model, it's best to access the original DEM rather than using this one. But if you just want a quick reference to see the basic topography that is driving some of your radiometric returns, this can be included as a convenient resource. You also have the option to include the incidence angle map and the scattering area maps, and these are most important if you will be doing higher level processing once you've generated your RTCs. Lastly, there's a speckle filter option. SAR has an inherent speckle characteristic, and it's due to the interference when returns are coming back from different scatterers. So you might have an area that should be pretty consistent in its returns, but you'll get these bright pixels or dark pixels where you don't expect them. And that's just due to the interference patterns. So there is an option to apply a speckle filter. We use an enhanced Lee filter, and it averages together the pixels so that it dampens down the effect of the speckle. It does mean that you lose some degree of resolution when you apply a speckle filter, so it will really depend on your particular application what works best. So again, you could try one with and one without. We also don't, at this point, give any opportunities to adjust the speckle filter that's applied, so it's just the one option of the enhanced Lee filter. So if you have selected all of your parameters, you can then submit submit the queue for processing. And those are sent off for processing, and at this point it brings up a link to view your on-demand products. You can view your on-demand products at any time by changing the search type to this on-demand products. This will show all of the products that I have processed, and you can see that for me that's 362. There are quite a few, and so it's getting a little bit messy. And so we have the opportunity to filter our on-demand products as well and search for just the things we're interested in. So I can search for the project name. So if I'm just looking at the products that I just submitted, here are those two pending products. They have been sent for processing, and once they start actually processing, they will change to running status. Once they're in running status, it takes about 20 to 40 minutes to generate these products. So you can come back, and once they're complete, you'll see that there's a zip file that's listed rather than the source granule. Once you have a zip file available, you can click on that, and there are some download options. Once the data set has been processed, you have 14 days to download it. After 14 days, we delete the data set, and the link is no longer active. It will still be listed in your results, however. So if I go to another project that has a bunch of expired products, they're all still listed for your reference. So if you wanted to go back and see what you processed in the past and reference that for another round of processing, it's there for you. But it can get a little bit distracting. So there's also the option to hide the expired products so that only the products that you have available for download will be displayed. So I can also apply additional filters to my results. Even in my Michigan demo project, there are quite a number of files. And so if I just want to see the files from, say, October, I can select that date range, and it turns out that I don't have any October files, so I will look at November as well. There we go. So I've got some September files in this project. So once I have those files, I have the option of either downloading them directly, so I can click on this button for each one, and it will just launch the download directly in my browser, or I can add that product to my downloads queue. So I can either add that here in the file information pane, or I can just click on it directly in this pane here. And I can click them again to remove them from the downloads. Similarly to the on-demand queue, I can also add these all at one time. When I open the downloads queue, you can see here are my two products that I wanted to download. I can again just click on them one at a time and download them. But if you do have Python installed on your computer, you can make use of a bulk download script. Now for two products, this isn't a huge deal, but if you had a longer list, it is nice to be able to launch that process and just let it run in the background while you're doing other things. So if I click the download, the Python script, I have a Python file that I can just launch. It will start a shell. Because I have used it recently, it just starts downloading. If you hadn't used it for a while, it would prompt you for your Earth data credentials again. And then once those are entered, it starts the download process. And that will just go through and download each one of the files in turn. And that can just be running in the background while I'm doing other things. So it's important to notice that if it will, this download script will download the products to wherever that script is located. So if you wanted to download all of your zip files into one area for a project, you could just move the Python script there and then run it from that location. And then you'd get all of your files being downloaded to that same spot. Otherwise, you can see that I've already downloaded one, and then here's my other one. I'm going to open up ArcGIS, and I have included also a link in the persistent links pod to our GIS tools website. And we do have a custom toolbox that's available for use in ArcGIS applications. And I'll just use that to unzip my files. So there's an unzip utility that allows me to set the location of those zip files. So I had just put them in my downloads folder. So I'll select the downloads folder, and then I will select a destination. So I will add a new folder and say, call it Wednesday, and download my files there. So this just extracts all of those zip archives into your new location, and it also deletes the original zip files. They're quite large files, and so it's good to kind of clean up after yourself after you have downloaded the data. So this process just extracts them all to the same location and deletes the original zip files. So if I go to my demo folder and refresh to see my new additions, I have a couple of RTC products. In each one of the folders, as I mentioned, there are a lot of different rasters that you can explore, but the key ones will be these geotiffs that are marked with the polarization. So I can bring in my VV RTC products, and once I build the pyramids, that data set will be added, and it's ready for use in a GIS application. And that is our on-demand processing functionality. I will turn it back over to Jennifer for the polling questions.
Okay, thank you, Heidi. Thanks, everybody. At this point, we will transition to the optional final set of polling questions. We'll keep these questions about 3 to 4 minutes or so, and then from there we'll transition to the Q&A period. We've actually received quite a few questions so far, and so we will try to address all of the questions during the Q&A session. But if we're not able to get to your question, please know that I will be sending the Q&A log to our speaker so that she may follow up with you individually offline. Okay, and I will attempt to address all questions in the order that they were received. All right, thanks everybody. Let's give these a few minutes and then we'll move to the Q&A. Okay, at this point, we will transition to the Q&A session. And for those of you who had asked about the presentation files, you should see in the lower right-hand corner of your screen, the first file is going to be today's presentation, which has the links embedded on the slides. Okay, so that's the first file. If you click on it, you'll be prompted with an opportunity to download the file. And then the agenda is the second file. All right, so let's get started here. We've had quite a few questions. So, give me just one moment. Okay. Okay, this is actually a question that was answered earlier, but the question was, do you process SAR data only for the United States? Is Canada covered? And it's not only for the United States, but I don't know, Heidi, if you wanted to say anything further about that.
Yeah, sure. So there is the coverage map. That's our current coverage. So Canada is covered, and we're mostly missing Greenland, Antarctica, and then the north of 60 part of Europe and Asia. But Sentinel-1 covers Canada. There is Sentinel-1 data. It's just and we can process that as well. Yeah, and there, yeah.
Okay, wonderful. So our next question is, I'm interested to know if SAR data, specifically Sentinel-1, can be used for crop hail damage assessment. Have you had any successful studies on crop hail damage, or is finer resolution SAR data, ICEYE, Capella, needed for accurate hail damage assessment?
So this is a very specific question. I think we'll probably focus more on general questions. There is, the answer to these questions is always pretty much it depends. So it will depend on the extent of the hail damage, whether Sentinel-1 is appropriate, and if the resolution that is available is appropriate for the particular amount of hail damage. If you are looking at a very specific area of interest and there's very localized damage, that would it would be difficult potentially to pick that up in a 30-meter product.
Okay, thank you, Heidi. The next question is, when we generate a 2D or 3D displacement map using, I don't know if it's DynSAR or DynSAR, could you please explain a little bit about the use of Tikhonov regularization, or L2, in which part is used, and it says why for what, and if it's reliable to do it with Sentinel-1. I'm not sure, there may be a couple of typos in here.
Well, yeah, so I would like to focus on the amplitude part. We didn't cover INSAR, and really that's a huge topic and a really dense topic. And so I don't, yeah, I'm sorry, I'm not prepared to answer an INSAR question with that level of specificity.
Okay, but we can get to these questions offline with the individual users. So the next question is, how about coverage for places in the equator region like Malaysia?
So there is Sentinel-1 coverage, certainly, and we do have the ability to process RTC over equatorial regions. It's really only areas above 60 degrees that are a problem, and below 60 degrees south.
Okay, great. Thank you, Heidi. The next question is the RTC product only available for Sentinel-1 data?
Currently, yes. We can only process with our on-demand workflow. It's only for Sentinel-1.
Okay, thank you, Heidi. The next question is, I'm working on Sentinel, so I'm not sure which questions to include or not. I'm working on Sentinel-1 C-band data for forest biomass estimation. Is it good? Is this a good, is that a good data set for measuring forest biomass?
Right. So the C-band sensor is a little bit difficult for forest biomass. And again, I'd like to focus more on kind of the on-demand questions, but I will address this quickly. The C-band does not penetrate very far into a dense canopy. And so if you're looking at a rainforest biomass estimation, you would be better served by a longer wavelength, something that has an L-band. would direct you to the SAR handbook, which has some really good information about doing biomass analysis and goes more deeply into that, more than I would have time to address today.
Okay, thank you, Heidi. Which DEM is used? 10-meter DEM for US, CDEM for Canada?
So for North America, so for most of our global coverage, it's the SRTM, and then for North America, we use the National Elevation Dataset, or what is now the 3DEP, but we use a fairly coarse resolution just because we are generating a 30-meter product. So yes, we will use the 1/3 arcsecond DEM for most of the United States, and then for other parts of North America, it kind of depends on where it is, whether it's the NED1, which is a 1 arcsecond or a 30-meter DEM, or the NED2, which is actually a 60-meter DEM. There are only a few places that are covered, and it's mostly in Alaska that are covered by the NED2.
Okay, thank you, Heidi. The next question is, for Sentinel-1 RTC products, have you measured the co-registration error between images? And if so, what are the average errors?
We haven't done an analysis to that extent. If you're interested in working with us on that, that would for sure get in touch.
Okay, great. The next question is, I'm really new to the RTC data, so what are the main application scenarios for RTC data?
Yeah, so if you're new to this, I do encourage you to check out the story map. It really kind of walks through a number of different scenarios and ways that you can be using the RTC data sets in very applied ways. Again, the SAR handbook also will have a lot of workflows that apply this data set in very specific ways, much more than I can go into in this short question and answer period. So the story map is available to anyone. You don't have to be, even though it's through the ArcGIS platform, you don't have to be an ArcGIS user or have credentials. Anyone can access that and work through the workflows.
Okay, thank you, Heidi. The next question is, for surfaces of glacier, which polarization is better to use, VV or VH? And about Sentinel-1 metadata, is heading platform, is this the same to the azimuth angle? So the first part of the question is which polarization is better to use for glacial surfaces, VV or VH? And then the second part was regarding the Sentinel-1 metadata, whether or not heading platform is the same as the azimuth angle.
Yeah, so I'd have to look at that second question. I'd have to look that up. I'm not familiar with all of the variables in the metadata that is being referenced, so we could potentially follow up on that later. In terms of the glacier applications, it really depends what you're looking for on the glacier. If you're trying to differentiate like surface water from ice, then the VV is probably going to be more useful depending on the characteristics of the ice. So some ice can actually, or some ice and snow layers can serve as a volume scatterer, or act as a volume scatterer. So it will really depend on the actual characteristics of the glaciers that you're looking at. So you'd have to experiment with that and see which one works best for your particular application.
Okay, thank you. The next question is, does RTC process Sentinel data still need geocoding?
No, it's all georeferenced. It's fully geocoded. It is in place. You can bring it into a GIS. It's ready to go.
All right, great. What is the difference between this pre-processed Sentinel-1 and GEE products?
Yeah, so the GEE products, the last that I looked, they were not radiometrically flattened, so that may have changed. The GEE platform is really dynamic. So the last time I looked, it was a terrain-corrected product, but not necessarily radiometrically corrected. So you don't have that normalization of the radar backscatter based on the slope area. So if anyone knows otherwise and wants to post that, that would be great. But to my knowledge, it is not radiometrically flattened.
Okay, thank you, Heidi. And give me just a moment here. Okay, the next question is, and I might need to go back a bit as well after this. Are Sentinel-1 RTC products appropriate for use within sub-pixel offset tracking workflows, such as the auto-rift tool that is maintained by JPL?
Could you read the first part of the question again?
Yes. Are Sentinel-1 RTC products appropriate for use within sub-pixel offset tracking workflows, such as the auto-rift tool that is maintained by JPL?
Yeah, so we are actually actively involved in the AutoRift project, and so Sentinel-1 data is being used in that environment. And actually, the AutoRift project uses fairly low resolution. Actually, it doesn't require a lot of high resolution just because of the scope of the project. So if you want more specific information, please do get in touch with us directly, and I can connect you with the people that are working on that project.
Okay, thank you, Heidi. At this point, we have entered the extended Q&A period. We have an additional 15 minutes. We're going to try to get through as many of these as possible. The next question is, which Sentinel data is the most applicable for fault in alignment mapping?
So fault mapping would, in general, be making use of an INSAR product. So you'd be looking at potentially movements. I'm not sure. I mean, it's a fairly general question, but if you're looking at movement along faults, that is more of a phase question rather than an amplitude question. On the other hand, sometimes you can see geographic features in an RTC product as well, but it depends on what you're actually trying to map.
Okay, thank you, Heidi. The next question is, so everybody has been muted, so if you're raising your hand, it would be better to ask the question within the Q&A pod, just to ensure the best audio experience. So the next question is there a plan to add the RTC for Elos Palsar?
So we actually, the Elos Palsar, we have RTC products already available, but we only are contracted with JAXA to host the original Elos dataset. So we don't, we're working towards adding potentially more Elos missions, but currently our dataset is mostly just the Elos 1, Palsar 1 dataset, and all of our Palsar datasets already have RTC products available, so you can just go to Vertex and search for a terrain-corrected product, and you can download RTC products. But again, that's just from the first Elos mission, so that's from 2006 to 2011. We hope to add more, but that's really, it's out of our hands. We archive and distribute the data that we have been given by NASA to archive and distribute. So we can't add additional data sets without that being in agreement with the source agency.
Okay, wonderful. Thank you, Heidi. The next question, I think if the participant wants to elaborate afterward in the Q&A pod, that would be fine. But the first part of the question is, are there available missions and current products, quad pole and L-band? And I'm not sure what the rest of this is meant to say. So
the current missions, so it's asking if there are current quad pole L-band missions. Am I reading that correctly?
Yes, quad pole and L-band, current products, available missions.
We at ASF don't have any of those products available. The Elos 4 or the Elos 2 mission, I believe, has some quad pole data over some areas, but we're not currently serving a large portion of that data, so I'm not familiar with it. There are potentially other data sets available that are not served through ASF, but we currently don't have any quad pole L-band mission data that we're serving. we will once the NISAR, well actually it's not quad pole, so the NISAR mission is an L-band mission that's coming up. The launch date is set for 2023, and that will be a NASA L-band mission. It will have like a pseudo quad pole, but it won't be collecting quad pole data, from what I understand, over large areas. So I'm not familiar with any like global quad pole data sets that are available at this point. But that's not to say they don't exist. I'm just not aware of them if they do.
Okay, thank you. Appreciate your response. The next question is, I have a question in the Speckle Filter part. I guess, which filter is at the moment used in the process? So this is actually referencing something that took place during the demo, I suspect.
Yes, so the Speckle filter that we're using is an enhanced Lee filter with a 7x7 window, and I believe, so the number of looks that is applied depends on the product. So the number of looks applied to a SLC product is going to be different than a GRD-derived product. So if you order a product and apply a Speckle filter, that information is listed in the XML file for the product. And so you can look through, and actually in the README as well, it would be referenced and would say how many looks were applied and all of the specifics of the filter. But essentially we use an enhanced Lee filter at 7x7, and the number of looks depends on the source data.
Okay, thank you, Heidi. And this is a perfect transition. What is the publication source used for the enhanced Lee filter? Is it Lopez and et al. 1990? You might not know that off the top of your head.
Yeah, I don't know that off the top. It's so we apply that filter through the Gamma software program, so we'd have to look at their specifications and what they're using to apply that filter.
Okay, thanks, Heidi. The next question is, can a DSM give advantages rather than a DTM when we process the data?
It depends on what you're looking for. So the digital terrain model, that strips it down basically, so you would be getting the elevation from a bare